Yes, okay. Earth science time. Today, we are talking about one of the most important, as I said, concepts, most useful concepts in earth science, which is mapping. We're talking about the philosophy behind mapping and also how mapping is done and why mapping is important in earth science. And so the first thing is, Cody, maybe you remember from physical science, but what is the first thing almost certainly that I'm going to, let's get rid of this. That's too cheerful. Too cheerful. What's the first thing I'm going to do? Whenever we're doing a discussion, what's probably the first thing we're going to do together?
Talk about the scales and quantities only.
More like, we're going to define this word. So what is a map? What is a map? Yeah, I mean, you know what a map is, but would you help me define a map in terms that will both apply to what we're talking about and make it easy for you to understand?
A model of land.
Perfect word. Model. I like that. A model, because as we talked about before, what's a model?
A model is like
a simplified version of a...
Yeah, you kind of interrupted someone, but that's all right. He was going to say that too. It's like what?
It's like a version of something.
Yes, exactly right. Simplified, as Will said, a version of, a representation is the word I would use, but a representation of, you said land. Does it have to be land? No. Let's put a model of Earth's surface. And even that, like a really easy counterexample would be that geologic map that we looked at, it did have some of what's under Earth's surface. So it's not always just the Earth's surface, but generally it is from what viewpoint? In what way are we viewing a map? As if it were what? Any map we look at, Google Maps, the geologic map, as you're looking at it as if you were looking down. Yeah, we're looking from, you might say, a bird's eye view. We call this, in earth science, we call it map view. When we're looking at a diagram or any representation and we're looking at it as if we were looking from the top down, we call that map view. And that's as opposed to, there's another term that we use a lot called cross-section, which we abbreviate XSect, but that's cross-section. So map view is from the top, we're looking at it as it were from the top, and in cross-sectional view, we're looking at it as it were from the side, usually a cutaway. So like we might have, if we had a cross-sectional view of a cake, we would see what the cake looks like from the inside. If we had a map view of a cake, we would see what the cake looks like from the top. Let's diagram that. That'll be a nice little diagram. When it was my son's birthday, Asher turned 5, and he had a Power Ranger cake. And in map view, the cake looked like this. Happy birthday! And it had little candles all over it, right? Map view. In cross-sectional view, the cake looked like this. Had layers, and it had candles, and it had a little bit of frosting, and frosting on the sides. This is cross-sectional. So you see the difference between, that's a very simplified example, but you see the difference between, in general, map view and cross-sectional view. So that's one of the most fundamental differences that we talk about with mapping. Now when we look at maps of the Earth in specific, here I have one. Here I have a physical map of the Earth. Do you see it? Does it show up on screen? I wonder. I'm going to have to go over here and look myself because no one's at the looking at table. Oh yeah, that looks great. There's way more of a glare in real life than there is on screen. So this is a map of the world. Now, first of all, let's start by saying remember, models are imperfect representations, right? This is a model of the Earth's surface, but it's imperfect. What are some imperfections? Now, we're going to list its imperfections. It's going to make us feel like it's totally worthless, as listing things imperfections does. But then we're going to talk about how it is still or even more useful because of those imperfections. Just like you, more beautiful because of your imperfections, right? That's what human beings are. So what are some imperfections with this map?
Size.
Yeah, so imperfect in the way that it is, maybe it's not inaccurate, although we are going to talk about that in a second, but this is not the same size as it is in real life. Would it be more useful if it were the same size as it is in real life? No. We would have just a whole separate Earth. I mean, first of all, we would have, to just produce this, we would have used all the Earth's materials, right? So that wouldn't work. So it actually, the imperfection, that's not, I'm putting that in quotes like it's pretend, the imperfection that it's not the same size as the original is actually a huge advantage, right? It fits in this room, so that's an advantage. We can see a representation of the way Earth is that fits in this room, and that's a real advantage. Okay, what's another imperfection about it?
It doesn't actually have the minerals that.
Yeah, the materials that this map is made out of are different from the materials that the Earth is made of. Okay, that's a good one. What else? Do you think this is an accurate representation of the size and shape of all the things on it? No. Well, how can you tell? What's the classic example? Do you know the classic example of how incorrect a map can be? If you look at even a globe representation, there you go, that's the one. Australia and Antarctica. And if you look at a globe, you can almost see, if this one were turned just a little bit, you can see that in real life, Antarctica and Australia are approximately the same size. There is a difference, but they're approximately the same size. Whereas on this map, and this one's actually better than a lot of them, it looks like Antarctica is the size at least of all of Asia and Europe, maybe even bigger. So that's a very classic example of how a map can be imperfect. And that's due to what's called the projection, which was one of your vocab words, and we will talk about that also in a second. What other imperfections do you see with this, if any?
There's letters everywhere.
Yeah, and so that's another, in real life, here's a really, I'm trying to remember which book it's in. There's a book I love, and it's a book about sailing, and there's a commander of a ship, and he's escorting a convoy of merchant ships, and he says that they are acting like they're going to trip over a line of latitude. And that's a little joke, because in reality, lines of latitude don't exist. He's saying they're sailing so slow they're afraid they might trip over something that doesn't even in reality exist. But the lines of latitude, even though they don't exist in real life, are extremely useful when we look at a map, right? They help us coordinate, just like the coordinate plane in math. They help us coordinate where locations are. And so they don't actually exist. Same thing with like the letter A here. You guys want to go on a field trip to find the letter A here in these? No, of course not. That doesn't exist. But again, even though that's an imperfection, it really helps us because that's labeling Africa that we might not know otherwise. And so we'll come back to this map today and also throughout this year. But understand that maps have, maybe imperfection is not exactly the right word, they have concessions that they concede to labels and lines of latitude and longitude and maybe slightly larger or smaller land masses in order to better show us the things that are true about the planet Earth. So we have a map there, and we have several things to talk about now about that map. So it's a model of Earth's surface. If it's flat, it needs to be projected. A map projection. The underlying principle of a map projection is that all of the pieces of, or whatever pieces you're studying about Earth for that particular map, are moved from a spherical object, the Earth, to a flat object, piece of paper, computer screen, whatever. One of a very nuanced way that you can try to help someone understand that the Earth is spherical. All the evidence that we have points to the Earth is spherical. This is not a video about conspiracy theories, but you know that some people insist that the Earth is flat, and that's kind of a new age thing where, I mean, that wasn't the case for many, many years, but now people think it's fun to pretend the Earth is flat. The pieces of evidence that the Earth is spherical are manifest. Like you can just, there are so many of them, but one of them, a nuanced one, is the map projection. If the Earth were flat, there would be no need for map projections and everything would be perfectly accurate on a flat piece of paper already, and it isn't. You can use, even on the scale of maps like the one Cody was using for his, that geologic map, if you don't account for the Earth's curvature, you will be off the map compared to real life by a certain amount every single time, and that's what people don't think about. But anyway, the map projection is a way of, the idea is that we have a spherical Earth here, and we need to get it onto a flat piece of paper, and so there's several ways. The most common way for the whole Earth is to use what's called a cylindrical projection. It's as if we wrapped the Earth in a cylinder of paper. Oh, I used to have a little squishy Earth. What happened to my little squishy Earth? I'm going to use your check-in sheet, Eli. It's as if we had the cylindrical or the spherical Earth here, and in order to get it onto a flat piece of paper, we just wrap the Earth up in it. And the reason it's called a projection is that we pretend like the Earth itself is harder than it looks. We pretend like the Earth itself is a light source, and that what's projected off of it gets shown on the inside of the paper. And so where do you think this projection would be very accurate? If we were shining light from the inside of planet Earth and it was showing up on the paper, where do you think this map would be the most accurate? Yes? Where specifically?
In the middle.
In the middle, exactly right. The kind of rule of thumb is that if we imagine the projection being made in this way, anywhere that's touching is going to be perfectly accurate. The light will shine perfectly, and anywhere where you can imagine if you have light shining out as shadows, they're going to be skewed towards the edges. And so here, this whole area up here and this whole area down here are actually points on Earth. This line on the top, right, when we unroll it, this whole line up here and this whole line down here were points on the spherical Earth. And so that's why Antarctica looks like that and the Arctic looks like that. So that one little point on Earth has become a line. That's a cylindrical projection. And there are variations of this. This one, if I remember right, it's called the Robertson projection. It says on here somewhere. It says on here somewhere. Winkle triple projection, which is that's so it tells you how it was projected. And actually, you'll notice that unlike, does Mr. Cakemaster have the one whole wall as a planet Earth? I can't remember. Somewhere in my life I've seen that. Maybe it's a different school. Does he have a giant map?
Yeah, he's got a giant map.
Is it just a plain square? Because a lot of times you'll see just an actual rectangle. And this one's a little better than the rectangle because you can see it kind of tapers towards the ends. And so instead of a line filling up the whole bottom, it's a slightly smaller line. So that's a cylindrical projection. And then if we have a similar situation here, we have the spherical Earth, and we, instead of a cylinder, we use a cone. This is called a conic projection. So here's a drawback with this one. Well, you tell me, what's a drawback with this one compared to the cylindrical projection? It doesn't have the whole Earth. So it might be useful for a single hemisphere or a single part of the Earth. And it's most accurate here, again, where it's touching. And by the way, both of these could be as small as you want. You don't have to do the whole Earth each time. But the conic projection is if we make a cone. This piece of paper is way too big for this Earth. Let me get a smaller piece of paper. Let me just fold this piece of paper. That'll be a smarter way to do it. This is just for the sake of the demonstration. It's not actually part of the... So here we have a conic projection. Now I've made it too small. There we go. So that's something like a... Come on, be a cone. Eli, your piece of paper is really bothering me. Okay, there we go. So it's kind of like a cone. Whoop. But we only get the part that's being covered by the paper. And it's most accurate where it's touching. And so it's actually least accurate near this point. So we unroll that and we get something that looks like that. Again, maybe that's the landmass there. But it's very accurate through the rest of this. And then another basic type that we use, probably the simplest type, is called a gnomonic projection. And what I've tried to indicate there is that it's just laid flat on it. This is called a gnomonic projection. Like that. It's just laid flat. And so it's inaccurate on the outsides, and it's only accurate at a single point in the middle.
What's that one called?
Gnomonic. G-N-O-M-I. Gnomonic. This should be the letter O. Gnomonic. Again, these up here now, these are mnemonic projections. So what this map has done by having these two in the corners here, which is kind of a neat idea, it knows the limitations of map projections. And so where here and here, this projection is inaccurate, it has these other separate projections so that you can see from the top and the bottom, as it were. And so for most of the Earth's land mass, and why do you think that that's what this map chooses to focus on, the land mass? Well, what's the alternative? If it's not a land mass, what is it? The ocean. The ocean. And so why would this map choose to focus on land mass over the ocean? Most of the time, right. That's where people live most of the time, is on the land. Now, for one thing, we wouldn't be using this map for ocean navigation. There are other better examples of that. And obviously, we would also probably want a smaller scale map as our, we would want, if we were cruising around in the Caribbean, we would want a map at the largest of just the Caribbean, right? We probably wouldn't use an entire world map to navigate the seas. But anyway, this map takes that into consideration and uses these two mnemonic projections for the northern and southern poles. So those are our kinds of map projection. And all of them incorporate lines of latitude and longitude. So on a rectangular, a cylindrical projection, the lines of latitude are horizontal, and the lines of longitude are vertical. So the latitudes, the way we remember this, it's kind of a silly way, but the way we can remember this is a latitude flat, longitude long. And that's a ridiculous way to remember because they're both flat and long. But we remember flat, latitude, long, longitude. On a cylindrical projection, they turn out to be a grid, like the coordinate grid, right? And so we might have something like, I don't know. By the way, we use reference points of the prime meridian, which goes through Greenwich in England, which is London, and the equator. Those are both 0 degrees. 0 degrees of longitude is the prime meridian, which goes through Greenwich in England, and 0 degrees latitude is the equator, which is the equator. And then we measure degrees west or east in longitude and north or south in latitude. And so we come up with, does anyone have their Chromebook handy? Or would you just look up the latitude and longitude for Crawford, Nebraska? Now, it just as an example, I can show you. And there's a couple different ways that we measure latitude and longitude, and by a couple, I mean, as far as I know, there are exactly 2. We do sometimes use what's called a UTM grid, which measures in meters west and east, or north and south of London and the equator, respectively. But in general, when you see coordinates, they will be in latitude and longitude. And I think actually, now that I say that, I think a UTM actually uses specific zones, and it measures degrees, or not degrees, meters east and west or north and south of the zone boundaries. And so if you're watching this video and you're a real UTM buff in the future, you can take my correction under advisement. You do sign into your Chromebook, and then we will end up with a coordinate that'll have the latitude first and then the longitude. It'll tell us degrees east or west, and then degrees north and south. While we're waiting on that, you'll see another thing about this map. We have, of course, the compass rose, which tells us north, south, east, and west, and that's about all I'm going to say about that, although you should be aware that there are ones in between, like northwest, and there's one in between like that like north-northwest, and there's ones in between that, like north-northwest and a half west, and so on. It gets more and more minute. The more it gets more granular, the more nuanced you want your measurements to be. But also there's this map scale, and the map scale measures any unit you choose to use. One of those on this, in this case, is 24 million in real life. This says down here, scale 1 to 24 million, or 1 inch equals 379 miles. And that says at the equator. And so because it varies, it's going to be different down here because of the projection. So at the equator, it scales 1 to 24,000, and it's in a unit. So this says 1 inch equals 379 miles because that's 1 to 224 million. But also, if we use just any, it doesn't even have to be unit, but one marker. So if it's a marker from Crawford, roughly Crawford, to the eastern coast of Maine, it looks like. That's one expo marker on this map. In real life, 24 million expo markers. So you think of this lined up 24 million times, that will get you to the east coast of Maine, okay? I mean, obviously, if it's something like a meter, slap, from Crawford to central Sumatra is about 1 meter on this map. In real life, 24 million meters, which is 24,000 kilometers. Does that kind of make sense? The map scale doesn't, it's unit less because it could be any unit as long as it's the same both times. Uh-oh. Yes, would you please? Uh-oh. Tell me the coordinates of Crawford.
42.68.
Oh, it's point. That's interesting. Go on, though. 42 point what?
6830 degrees north. And 103.4055 degrees west.
I'm interested in this because this is called decimal degrees. Another way that it can be represented is in minutes and seconds. So it might be like, did you find that on Google? Would you just type in minutes and seconds after that? Exactly what you typed in, but just type in minutes and seconds. So now you'll probably find, what? Scroll down a little. What? How did it not get any results? Oh, it's probably because of the network filtering. You only get certain websites. Hold on. That is so weird. This is such a strange Google search to me. Okay, we'll just talk about this for a second because I don't have the brain power to convert to minutes and seconds in my mind. The more old-timey and still somewhat common way of doing this is that you'll sometimes see something like 18 degrees, 30 seconds, 30 minutes and 10 seconds north, 69 degrees, 23 minutes and 12 seconds west. And what these are is that just like in an hour, there are 60 minutes, and in a minute there are 60 seconds. In a degree on the map, we can break that degree up into 60 minutes and those minutes up into 60 seconds. And this is not speed. This is not time. It's just another way of breaking up Earth's surface. This is called degrees, minutes, seconds, DMS, and this one is called decimal degree. So instead of being tenths, hundredths, and thousandths of a degree, these are 60ths, and these are 60ths of that, or 36 hundredths of this. There's just two different ways of representing it. When I was in earth science in college, we learned how to convert between these two. But honestly, I don't think that's useful for you guys. I think that most of the time we'll be using one or the other, and we'll just kind of stick with it. And usually it'll be this one. It's a little bit easier for people to understand, usually. You guys are used to using decimal math nowadays. And so whereas this makes more sense I think this is still often used in astronomy too, by the way, but from the perspective of someone who's used to working in base 60, this does make more sense. All right, once you're used to it, I guess it makes more sense either way. Oh, and another thing is that sometimes instead of saying east and west, these can be positive or negative. And so north of the equator is positive, and west of the prime meridian, east of the prime meridian is positive. And so sometimes you might see the coordinates of Crawford as 42.683, comma, negative 103.405. So we can do it without putting east and west if we use negative. So north is positive and east is positive. And so since Crawford is west of the prime meridian, it would be negative in that scale or in that system. We talked about map scale. Do you have questions about any of this? So this is all like the basics of mapping, and this comes up repeatedly throughout the year. I think that's about. Oh, your book does talk a lot about time zones. I'm going to trust you to either probably already know about it, but I'm going to trust you to either, if you don't know about it, just either read in your book or do some research on your own while you're working on your chapter review, but time zones is in here also. Do you have any questions about the mapping that we have talked about? Okay. Bye.